Okay, let's continue with the details of the factors that are affecting the corona. Coming to the size of the conductor, the corona loss is directly proportional to the square root of the radius of the conductor. Okay, so it appears that loss is more if the size of the conductor is more, but for large size conductors, VD, that is critical disruptive voltage, is more. For large size conductor, VD is more. Therefore, the term V minus VD is less. Therefore, the corona loss will be less. Therefore, the effect of VD is more dominant than the factor of under root radius of the conductor. Hence, higher the size of the conductor, lower is the corona loss. Okay. Coming to the surface conditions. The corona depends on the surface conditions of the conductor. For rough and uneven surfaces, the value of the disruptive voltage is less and corona effect is dominant. Similarly, corona loss is also more for rough and dirty surfaces. Coming to the number of conductors per phase, for higher voltages, a single conductor per phase produces large corona loss. Remember, for higher voltages, a single conductor per phase produces large corona loss. Therefore, we go for bundled conductors. With bundled conductors, the self GMD, that is geometrical mean diameter of the conductor, and the delta, that is your what is that? Delta is equal to 3.92 p. It's a factor that also increases, which increases the disruptive voltage and which reduces the corona loss. Okay. Okay, and next, coming to the spacing between the conductors. If the spacing is made very large, that is, spacing between two conductors is very large, corona can be minimized or it can be eliminated. But practically the spacing between the two conductors cannot be made too large. There is some limitation. Practically the spacing is selected so that corona is tolerable. Okay, there is a corona. We cannot eliminate the corona. Okay, and coming to the next 8-point, shape of the conductors. The shape of the conductors, like flat, oval, cylindrical, etc., affects the corona loss. For uniform cylindrical shape, corona loss is less compared to any other shape. Therefore, we always prefer cylindrical shaped conductors. Okay? And then coming to the clearance from the ground. The height of the conductors from the ground also affects the corona loss. The smaller the clearance, that is the clearance between the ground and the conductor, is less, then corona loss will be high. Therefore, we have to maintain a certain minimum distance between the conductor and the ground. The last one is the effect of the load current. As the load current increases, the temperature of the conductor also increases, and because of the temperature of the conductor increases, this will not allow snow, dew or dirt to deposit on the surface of the conductor. Therefore, this will reduce the corona loss. Due to all these factors, for a long transmission lines, the corona loss per kilometer of line at various points is obtained, and the net corona loss is obtained by taking average of all the values. Okay. Next, coming to the methods of reducing corona effect. So there are few factors that can be methods, or there are few methods that if you use them will reduce the corona effect. The corona effects can be, effects are observed when the operating voltage is more than, what is that? Critical disruptive voltage, that is usually around 30 or 33 kilovolts. So we will use some of the methods, the following methods, to reduce the corona effect. First one is by reducing, by increasing the value of the conductor size, by increasing the conductor size. By increasing the size of the conductor, disruptive voltage is increased. Hence, corona effects are reduced. If disruptive voltage, that is VD, is increased, the term V minus VD square, what will happen? It will decrease. If it decreases, then what will happen? The power loss also decreases. That is, corona effect gets reduced. Thus, conductors with large cross-sectional area like ACSR, what we have discussed, all conductor, aluminum conductor, steel reinforced, ACSR, aluminum conductor, steel reinforced, such conductors are used so that the effect of the corona can be reduced. Second point is by increasing the spacing between the conductors. The increased spacing increases the voltage level at which corona starts. Understanding? If we increase the spacing between the conductors, then what will happen? The voltage at which the corona occurs will increase. Thus, the corona effects can be minimized. But practically, spacing cannot be increased beyond certain limits, as the cost of the supporting structure also increases with increased spacing. Okay. Third point is using hollow and bundled conductors. So, the hollow and the bundled conductors will reduce corona effect. Okay. Next, we will solve some problems based on corona. Okay. Okay. Shall I write, or okay, I will write the problem and then you try to solve that problem. Okay. A three-phase line. A three-phase line has conductors of 2 centimeter in diameter. As conductors of 2 centimeter in diameter and spaced equilaterally equilaterally 1 meter apart. Okay. If the dielectric strength of the air is 30 kilovolts, for the line, which is maximum. 30 kilovolts per line that is maximum per centimeter. Find the disruptive critical voltage. Find the disruptive critical voltage for the line. Take a density factor, as 0.952 and irregularity factor as 0.9. Okay, so this is the problem statement. Now let us solve this problem. Okay, first write down conductor radius. Conductor radius is, what is that? Diameter is given, therefore radius is 2 divided by 2, which is nothing but 1 centimeter. Next, spacing between the two conductors he has given, which is equal to to 1 meter, but it should be converted into centimeter, therefore 1 meter is equal to 100 centimeter. Okay, then what else he has given? Dielectric strength of the air. Dielectric strength of air he has given. Dielectric strength is, what is that? G0, isn't it? G0. What is that? G0? 30 kilovolt per centimeter, which is nothing but 21.1 kilovolt per centimeter. What is that? RMS. Okay, this is maximum. Fine. Okay. Now, what else he has given? Air density factor he has given. What is that air density factor? Air density factor is delta. Air density factor is delta. Okay. What is the delta? Delta, what he has given? 0.952. Okay. And he has given M0. Irregularity factor also is given. What is that? M0. M0 is given how much? 0.9. Okay. Fine. These are the things he has given. Fine. What he has asked? He has asked you to calculate. He has asked you to calculate what is the critical disruptive voltage. That is VD. VD